All right, welcome. So we are recording Private Pilot Ground School. Gosh, what is today? Wednesday, April the 8th. We see Chance making it in after all, so we'll go ahead and give Chance in the grade book there for attendance. And we're just keeping our eyes open for Charles or Dylan as they might possibly show up. We've been reviewing our midterm test. We are just about done with that. We're like on question maybe 66 out of 70. So it's not going to be a whole lot of time that we're going to spend reviewing the midterm. I've been spending more time grading and going through everybody's midterm. Some positive things is that I'm seeing a lot better test grades using this distance format. You know, I'd like to think it's because everybody's studying so hard with their extra time and really learning the material, and awesome, way to go. You know, just, word to the wise, if anybody out there is, doing something unethical, looking up answers, got their book open, just be really careful, because that's, it might help you in this class on the grade, but it's not going to help you when you have to take the real FAA written exam. So the real FAA written exam is going to be a proctored exam where you will have a test proctor making sure that it is, closed book and closed notes. Historically, with the university, that has been a deal we do during finals week, where we take you all to the computer lab and one by one we administer the tests to you. With everything that's going on now, social distancing, I'm not sure what the strategy is going to be. My boss is telling me to hold on, hang on, wait. We're not certain yet. It could be a possibility that the end of the semester we might be able to get together and accomplish that goal. It also could be a possibility that the university would issue you endorsements, and then if you have the written endorsement, you can then take that written endorsement to a testing center, and then you could possibly take the test that way. So the answer is I don't know. I'm just throwing out possible options of what might possibly be the outcome when it is time to take the written test. Until then, we'll just, keep covering our material, take our tests on Blackboard, and just realize that this material, is something you're going to need to put in the back of your brain, not on a piece of paper or in the book, because there will be a real test eventually, whether we're able to give it to you through the university at the end of the semester, or whether we have to issue you an endorsement to allow you to take it at another testing center somewhere else. If you have questions about that, I don't mind addressing them, but the answer is I don't know. We're still waiting on the boss's guidance. I think for the state of Indiana, I think the current governor recommendation is May 1st. So I think that's when we're currently looking at possibly flying airplanes again, and that's when we're currently getting the idea of maybe possibly returning to a normal operation. Happy Wednesday, welcome. If anybody has any general questions or thoughts for the group, now might be a good time, unless you want to jump into reviewing some of those test questions. We're getting a lot of feedback here. All right, well, I guess that means everybody wants to go ahead and check out some test questions. We were working on some math problems when we last left. We were talking about some Zulu time and time zone conversions. So let's see if I can hit share screen. And at this point, you all should be seeing our midterm exam. Oh gosh, but it's the wrong. We're not trying to take it, we're trying to review it. Gosh. So here it is, and I need to click the button that says edit the test. I hit the wrong button. I need to hit edit the test. And of course, the computer seems to take a longer amount of time when we're streaming. So just to warm your brain up and start thinking about this topic, we're talking about UTC, Universal Time Coordinated. That is Zulu time. Right now in Indiana, we are 5 hours away from Zulu time. So if your current time local is 10:30 in the morning, add 5, it's actually 15:30 Zulu. So the current Zulu time is 15:30. So we are 5 hours away from Zulu. Why is this so important? Because you might be flying to an airport that is in a different time zone. And then all of a sudden it becomes confusing if everybody has different time zones. So when we do flight planning, when we talk to flight service station, when we file flight plans, we're supposed to do all of our time information off of Zulu clock, UTC, Universal Time Coordinated. So this is where we left off last time. I'm trying to zoom in so we can get a nice good picture of it, zoomed up for you, everybody to see. Question 66 is coming right up. Oh, look at that beautiful picture of the United States of America. Just makes us proud. So we have a question that says, an aircraft departs Mountain Standard Time Zone, 1650 MST, Mountain Standard Time. The flight's going to be 2 hours, 15 minutes to an airport located in Pacific Standard Time Zone. All right. The estimated time of arrival at the destination airport should be. Okay. So underneath my mouse, here is where it's explaining the different conversions. I can actually scroll up and show you. We're going to depart Mountain Standard Time Zone, so hanging out here with the Rocky Mountains, and we're going to go flying west into Pacific Standard Time Zone. Cool, awesome. So we're going to go from Mountain to Pacific. We're going to go west. I get it. We're starting our flight at 1615 Mountain Standard Time Zone. So here's your little legend. It says to convert from Mountain Standard Time, add 7 hours. All right. So I was at 1615 Mountain Standard Time. We need to add 7 hours. So, 16, I go 17, 18, 19, 20, 21, 22, 23. So I'm at 23. So 16 plus 7 is 23. So we depart at 23:15. We depart at 23:15 Zulu time. And if I was a way that I could write on the screen, I would do that. Annotate. Okay, I've never done this before. Tell me if you guys can check this out. So we started at 16. Oh gosh. There you go. We started at 16. Ah, that was a bad move, huh? I'm sorry about that one. Gosh. There it is. It's gone. We're going to try again. Oh, here's text. Maybe that'll be easier. Text. Click the button. We started at 16:15 MST. Is everybody seeing this? Any feedback would be great.
Yeah, that's good.
Yeah.
Cool. So we started at 16:15 Mountain Standard Time. We're going to add Mountain Standard Time 7 hours. 7 hours as a conversion factor. And so that's going to put us, we said 23:15 Zulu time. We'll call it UTC. And that's going to be our departure time. Okay, so hopefully you're following this. It says the flight's going to last 2 hours and 15 minutes. So we're going to add 2 hours, 15 minutes for the flight. So then it's going to be, I did this wrong. This is supposed to be 23:15. Does that look better?
Yeah, it looks better.
So that means we're going to arrive at 25:15 UTC arrival. But wait, there's no such thing as 25:15. 25:15, because there's only 24 hours a day. So like when it's actually 25, that means we're actually talking about 1 a.m., 1:15 a.m. Zulu. So I could convert that over and call it 01:15 for our arrival, but I know because I've looked at this problem that I'm about to have to do more math, so there's actually no reason to do that conversion yet. I'm gonna see if I can move this over out of our way. There we go. Okay, so you call it 25:15 Zulu. It's AKA also known as 01:15 Zulu UTC. Regardless, we now know what time we arrived in our California location, called that Pacific Standard Time. So if we want to know what time we're going to arrive in the Pacific Standard Time, it would be 1:15 Zulu. But what would that be local time for the California folk? So it says Pacific Standard Time, you add 8 hours. And that's how you convert, if you read the legend, to convert from Pacific Standard Time to Coordinated Universal Time, you add 8. But wait a minute, we're doing the opposite. We're trying to convert from Zulu time, Coordinated Universal Time, we're trying to convert that into Pacific Standard Time. So we actually would subtract 8 hours. So if you subtract 8 for our UTC conversion factor, that would mean we would take 8 away from 25. We're at, what, 17? 15 Pacific Standard Time arrival. All right, there's all my math. That worked out way nicer than I thought it was going to. So if I can scroll down, how do I stop formatting mouse? Well, that's not very handy, huh? There we go. Oh, gosh, look at that. I screwed up our math. We said the flight was 2 hours and, We're close. Gosh, can't win them all. So I screwed up some of our numbers here. I am so sorry. I wish I could fix this. But so we did 23:15. That was our Zulu departure time. We had a 2 hour, 15-minute flight. So our arrival time should actually be 25:30. I screwed that number right up there. It says 25:15. It should be 25:30. We arrived 25:30, which would really be 01:30 Zulu. And then you subtract 8 hours for the conversion factor for Zulu time. And so we'd actually be arriving at 17:30 Pacific Standard Time. Should I retype all that out, or does that make sense? Or what do you guys think?
You're good. It made sense.
Yeah, it made sense.
All right, so I think I can hit this clear button, maybe clear all drawings. All right, well, that was kind of a cool little tool. X. All right, now I get back to, cool. So those are some Zulu math problems. It may seem tricky, it may seem intimidating. It's not that difficult. There's more than one way to skin a cat. There's more than one way to do math problems. So you ask 10 different pilots, you're gonna get 10 different answers of what's the best way to do these math problems. My guidance is to do it just like I did right there, which means you kind of take longhand, you add a few extra steps, you convert everything to Zulu and then convert everything back to local. All right, we'll keep moving unless somebody wants to speak up. And looks like now we're looking at a problem that has extra steps, extra figures, extra charts. So we're studying this sectional chart, figure 22, and we're studying this AFD chart supplement, facilities directory, figure 31. Okay, what is the correct Unicom frequency to be used at this French airport, Coeur d'Alene? If anybody knows French, feel free to help me out. We want to request fuel. So we need to request fuel from this airport. We need to know the Unicom frequency. We actually could look at either one of these figures to figure it out. When we're looking at the sectional chart, it's called Area 2. And then when we're looking at figure 1, it's just the airport, Coeur d'Alene. So here's Area 2, and here's our airport in question. This airport in question, here's the name of the airport. The identifier is Charlie Oscar Echo. They have an AWOS, that's an Automated Weather Observation Station, the weather machine on 13507. You don't have to say the last 5, but you can. Their field elevation looks to be 2,300, MSL, It looks like their longest runway is 7,400 feet. And then their CTAF frequency is 122.8, 122.8, and it's a C in a circle for their CTAF. That is the very last frequency that is notated. So typically the very last frequency notated is the Unicom frequency. And it just so happens that it is both the Unicom and C in a circle CTAF frequency. And furthermore, it's showing you here they have RP, they have a right traffic pattern for a runway. It's really difficult to see, maybe runway 7. So right here, I can already tell you that I'm leaning towards the answer of 122.8. It's the only frequency here that you can talk over top of. They have another frequency, 135.07, but that's the weather station. So you don't want to try to talk over top of the weather station. So 122.8 is the best answer that I'm getting looking at this sectional chart. Furthermore, I can verify that answer by looking at the airport facilities directory. If it was the day of the actual written, I probably wouldn't even reference this chart. I would just go ahead and click 122.8 and move on because that's a timed test. But today we're learning and we're practicing. So we're studying this airport facilities directory chart supplement. And right here, it tells you clear as day. Communications frequency, CTAF/Unicom, 122.8. So that's why we get the correct answer of 122.8. While we're here, we always want to stay sharp on our airspace. So a quick review, we have a dashed magenta. That means the echo airspace begins at the surface. Right here, we have a fuzzy shaded magenta. That means the division line between Gulf airspace near the ground and echo airspace above is 700 AGL, 700 AGL. Over here, we have an airport without any fuzzy magenta. So that means the division line between the Gulf airspace below and the echo airspace above is 1,200 AGL. There's a 6.6 right here. That's called minimum quadrant altitude. So you imagine this quadrant here. If you were going to fly your airplane in this quadrant, you would be safe if you flew 6,600 feet. You would not hit any obstacles. You would clear all the obstacles in this quadrant by a minimum of 100 feet if you flew at 6,600 MSL. Just reviewing this line here, 14 degrees, 30 east. That's called minutes, 14 degrees, 30 minutes east. This is a line of variation. You can call that an isogonic line. And remember, we talked about like deviation and variation and reasons why the compass may not be accurate. This one is variation. It's a line of variation, an isogonic line. A lot of people say east is least, west is best. It's a phrase you're going to hear a lot of pilots say. East is least, west is best. So when you do math, when you do flight planning, you would actually subtract 14.5 degrees from your magnetic heading. I should say your magnetic course is what I should have said. You would subtract 14 degrees, 30 minutes, 14.5 from your magnetic course. And that's going to, it's from your true course, really. Yeah, you subtract it from your true course to get your magnetic course. So the final answer, this is a line of variation, and it's going to help you with flight planning and more math problems for this written exam, because when you cross this line or anywhere in this area, let's say that anywhere in this area, you need to do math to make your flight planning more accurate because the compass is inaccurate in this area. It's off by 14.5 degrees. Call it 14 degrees. So you would subtract 14 degrees. Why? East. East is least, west is best. If the line is labeled E, then we subtract. If the line was labeled W, we would add. East is least, west is best. We subtract 14 degrees from our true course, and that would give us a more accurate magnetic course for when we use our magnetic compass. You don't hear a lot about that a lot here in Indiana because we're very close to the 0 degree line of variation. We're only off by a few degrees in Indiana. But when you start getting out west in Alaska, it becomes very large numbers. So it was a good teachable moment for us. We're always trying to recall everything we can about these sectional charts. Every sectional chart has a new lesson for us. I'm not really seeing a whole lot of other tricky questions on here. If anybody has anything, feel free, but I'll keep moving slowly. All right. So we got a new question. Hooray, new question. We got ATIS, ATIS, Automatic Terminal Information Service, is the continuous broadcast of recorded information concerning non-control information in selected high activity terminal areas. That is the correct answer. So I have some of y'all clicking this incorrect answer, this incorrect distractor. Pilots of radar identified aircraft whose aircraft is in dangerous proximity to terrain or obstruction. Well, anybody can tune up the ATIS station. Anybody could tune up and listen to the weather report, could listen to the runway closures. Anybody can tune up to that. So whether your aircraft is in radar contact, whether you're squawking or talking, it's irrelevant. So this one doesn't really matter at all. Non-essential information to reduce frequency congestion. That's actually a really good answer. I really like that answer. This is a very good answer because it's the fact that it says to reduce frequency congestion. And that's exactly what ATIS is about. The air traffic controller does not want to have to repeat what runways are closed, what runways are the active runway, what taxiways are closed, what the winds are, what the pressure setting is. The air traffic controller does not want to have to repeat that to every new airplane that hops on the frequency to say, you know, good morning. So the idea is that this is a very good looking answer, choice B, but it's not correct because it says the word non-essential. So the air traffic controller would argue that it is essential information to know what the active runway is, what the current wind conditions are. Okay, this is one of the most missed questions on the test. And it kind of saddens me because this is like really basic private pilot stuff. And this is like really what we need to be spending our time on. So, you know, I'm just having a heart-to-heart with you guys. I'll stop the share. I'm having a heart-to-heart with everybody right now. We as pilots, like one of the biggest things that we need to really get straight and really understand is like north, south, east, and west. Like, you know, there are a lot of people that drive cars and they drive the car and they have no idea which way they're going or how they ever get anywhere. They just turn on the GPS app, and you might be one of those people. I mean, you know, I'm guilty. I've done it before. You know, I'm in an unfamiliar place. Gosh, I'm turned around. I put on the GPS app. But unfortunately, that's really not the way we're supposed to be in the airplane. And we really don't want to be creating pilots that don't know how to navigate or don't know the difference of north, south, east, and west, and they just follow the GPS all the time. One of the best things that you and your instructor can do when you guys go fly the airplane is take that moving map GPS display and twist the knob a few times and get to the traffic screen so you don't see the moving map display. You gotta train and practice your ability to look out the window, to use the compass, to look at the landmarks out the window. So today I'm going to walk you through this problem, but this is kind of one of the really fundamentals that we as pilots need to focus on. Questions like this, and the other questions that I'm seeing a lot of people miss, like how do you know which is the correct runway to select? You know, trying to figure out which direction the wind is from, headwind versus tailwind. So we're going to spend some time on this one. It shouldn't be too difficult, shouldn't be too crazy. So let's try to use this annotate feature again. So I'm going to try to draw again. Okay, I'm gonna figure it out, I promise. Here we go. Oh yeah, look at that. It's looking good. I can almost draw a perfect circle with my mouse pad. Cool. So here's my cardinal headings. So this will be north. Oh my gosh, maybe the type tool would be better here. This will be north 360. This one over here is going to be east. Oh, it didn't work. East 090. Down here will be our south 180. And over here is going to be our west 270. Everybody see it? Everybody's with me? Okay, I'm going to keep going. Thank you. Thank you for the feedback. Thank you. Okay. An air traffic control facility, radar facility, issues the following advisory to a pilot flying on the heading of 090. So let's stop. We're going to draw. Okay. I'm still on text tool. I want to draw. Okay. So our pilot, that's you. Gosh. This will work. This will work. Oh, yeah. I wish this wing was better, but everybody's with me. This is an airplane that is pointed easterly. Not bad. Not bad. Okay, so we got an aircraft that is pointed easterly. Let's go back to the text again. An air traffic control radar facility issues the following advisory to pilot on the heading of 090. So here you are, and you're flying easterly, 090. The air traffic controller says, traffic, 3 o'clock, 2 miles westbound. Where should the pilot look for this traffic? So the idea is that the air traffic controller is warning you that you have traffic at 3 o'clock. 3 o'clock means off your right wing. This is one of the most missed questions on the test. So if that pilot looks straight ahead, that's called 12 o'clock. If that pilot looks slightly to the right, that would be 1 o'clock. If the pilot looks slightly more to the right, that would be 2 o'clock. And when the pilot looks directly off the right wingtip, that would be called 3 o'clock. So if you're supposed to look over here off your right wingtip, that would be in the southerly direction. This is one of the most missed questions on the test. I'm trying to make it as clear as possible. Is this help? Does it hurt? Are there questions?
It's helping.
Helping. Awesome. So I'm quizzing you. I'm quizzing you right now. Who can answer me? If the air traffic controller said traffic at 3 o'clock, what direct? Oh, damn it. I screwed it up. Let's try again. If the air traffic controller said traffic at your 9 o'clock, if the air traffic controller said traffic at your 9 o'clock, what direction would you look?
North.
That's it. You would look to the north and you would look to your left. Okay. Okay. All right. So we're getting better with that. I'm going to push the clear button. Clear all my drawings, and I'm going to get back to the mouse. Awesome. Cool. Okay, we'll keep moving. From whom should a departing VFR aircraft request traffic information during ground operations? I don't like this question. The only reason I put this question on here is I want to prepare you for the real written exam. I see people selecting all 3 answers, and I don't think any of them are bad answers. I mean, I think that you really could probably ask anybody. But if I'm trying to help you pass the written exam, the most correct answer today is ground control. We have to try to figure out, why do we think ground control is the most correct answer? The FAA believes that because they're saying during ground operations. So from whom should departing VFR aircraft, so really just who should a VFR aircraft request radar traffic information during ground operations? Gosh, I think it's a really rough question. I don't like it. What can I do to help you? Try to see the word ground operations and think about how maybe ground control is who's going to give you traffic information during ground operations. So in the real world, I think any 3 of those choices could be fine. I think any 3 of those choices could be fine. You can talk to those air traffic controllers, they can help you out. But for the sake of the written exam, when you see this question about ground operations, think about ground control, and hopefully that'll help us out. All right, I think this might be our last question here. If we have an operable 4096 code transponder with an encoding altimeter, so when is that going to be required? What kind of airspace? So basically the question is, what airspace you need to legally have a transponder? So Alpha airspace, Bravo airspace, and when we're within 30 miles of the Bravo airspace, and Charlie airspace. That's the correct answer. Why Why is Delta incorrect? Because Delta, think D, dialogue, the only entry requirements you need for Delta airspace is 2A radio communication. They got to say your tail number back. Echo airspace, below 10,000? No, transponder is not required. You could have an old antique airplane going out and fly in the practice area, never talk to anybody, doesn't even need a transponder. Echo airspace. When you get above 10,000 MSL, then yes, you do need a transponder legally. Same conversation here. Delta airspace, all you need is dialogue enter. And G. G is uncontrolled airspace. G, near the ground, go kill yourself minimums, 1 mile clear clouds. So the idea is that the Gulf airspace does not require a transponder. So that was us reviewing chapter 1 through 5, midterm test. If anybody has any questions, thoughts, or feedback, now might be a good time for it. Our next step is going to be moving to weather.
Quick question. It's not about the test. It's about the email we got from the VU administration.
Okay, I'm listening.
It said there were like 5 different options. It was pass, fail, letter grade. There was something else. I was just kind of curious what that was all really about, because it was talking about like flexible grading options.
Yeah, so I don't want to lie to you. I'm going to tell you I'm going to start my conversation by saying I'm not sure. I tell you that I know that, so I have to input grades for midterms. I have to input grades for final grades. And you all should have a midterm grade for this class. So I have, we did that before break. And when I am submitting midterm grades as instructor, I have all those options available to me. And so there are some courses that are set up to be pass fail. There are some courses that are set up to be letter grades, A, B, C, D, F. There are some courses that are set up to be audit only. Like you could take a course and pay a reduced amount and audit the course, and then you never actually take tests or receive credit, but you could still learn the information and audit only. So it's kind of the fact that I think that there are a lot of different options that instructors can choose when they assign grades for students. I think a lot of PE courses are that way. So like if you take a PE course, like physical education, where you're supposed to go run laps and walk and go bowling or whatever physical activity, a lot of those courses are kind of set up like pass or fail. It's not the fact you get an A, B, or C, or D. Either you did it or you didn't. You pass or you fail. So I wonder, because I don't know, I wonder if it's the fact that with all this distance education that there might be some other courses where the instructor doesn't feel like they have enough information to be able to give letter grade of A, B, C, D, F. Maybe in some of those situations, the instructor, the course might have other flexible options to change their format and suddenly be a pass fail or audit or satisfactory unsatisfactory instead of necessarily letter grades. I'm not certain. I think it's just the university's trying everything they can right now to solve any possible problems that are arising. But the problem with us is that, this is a class that is required for your major. So for you to become, aviation flight degree, you have to pass this class with a C or better. So if you get a D in this class, it's really the same thing as getting an F almost. Not really, but if you get a D, then that credit would not count towards the major. You might still be able to take that credit and transfer it to another university for a different major as some general studies credit. But to be in the flight program and to get a flight degree, private pilot is a required course, and for courses that are in your major, you need to earn a C or better. So I hear your question. I'm not 100% sure of all the answers associated with it. For our course, we're going to be continuing to give letter grades A, B, C, D, E, there's no E, I'm sorry, A, B, C, D, F. But maybe that gives you more insight into the, the processes of higher education. And if anybody has any input to add, I mean, feel free. I'm not the expert. Is that what you were thinking? Yeah.
Yeah, I was just trying to figure it out because it just said VU emergency grading option because of the coronavirus. So I was just kind of curious.
Yeah, I think another option is like extension, not necessarily for us. I don't think we have that option of extension. That's not something I'm talking about. But, like your flight courses, like when your flight course happens, you were supposed to have completed 40 hours of flying. You're supposed to have completed so many stage checks. There's so many milestones that you were supposed to make in this lab-based course of the flight course one-on-one with your flight instructor. Well, snap, if they're shutting down all of our flight operations, then you're not going to be able to achieve those goals. So what's going to happen is that when the end of the semester comes and your flight instructor has to log into the Vincennes website and click what grade you get, there might be some other options for that instructor to click that might involve not issuing a grade, or might involve extension, or might involve some other, like we're saying, emergency flexible grading option when grades are due. But for us in our class, I don't anticipate having any of those issues. I anticipate that we're going to try to keep our schedule. I anticipate that we're going to keep trying to take tests and homeworks, and we'll issue letter grades, A, B, C, D, F.
Sounds good. I was just curious.
Yeah, I appreciate you asking. This is exactly what it's about, chance for us to get together and hash out thoughts, questions, and comments. Since I have everybody here and you're having to listen to the sound of my voice anyway, something that the boss, our chief flight instructor, is tasked me to do is to reiterate, re-emphasize to everybody that the VU students are not allowed to be in any of the VU facilities right now. I'm not sure the story. I'm not sure why. I don't think anything's really changed, but for whatever reason, I've been instructed to double communicate with you. So I sent it on an announcement. It should have came to you as an email. I mention it verbally out loud right now that, you as a VU student are not supposed to be, setting foot inside the Eagle Creek Airport facilities. You're not supposed to be setting foot inside the Aviation Technology Center facilities at the International Airport. So any sort of VU property, any sort of VU facility, we're not supposed to have any VU students allowed in there at this current time. So I think that was already communicated. I think everybody already understood that, but for some reason my boss asked me to re-emphasize that to everybody. Hooray for administrative announcements. Anybody got any good airplane jokes? Any good flight jokes? What happened to the pilot when he got in trouble? Nobody?
I have no idea.
He got grounded.
Oh my God.
Ah, good one.
It's the most interaction I've gotten all semester. It's good.
Wow.
All right. So I'm going to click some buttons on my end. I'm getting out of our midterm exam. I'm going to see if we can load up our new topic. Hooray for new topics. We have a new topic of weather. It's going to work. I know it. So I hit this button, screen share. Okay, so now you see my Blackboard, but for some reason, I'm not getting my list. Maybe I need to zoom out more. It's really small. So we're getting involved into weather. The new topic is weather. So as a aviation student, you're going to have two different focus points for the conversation of weather. We have weather theory and we have weather products. So basically that's chapter 6 and chapter 7 is going to be kind of your weather theory versus weather products. I anticipate that we will probably have a test that is chapter 6 and 7 together. So I anticipate that we will probably have chapter 6 and 7 together. So it'll be like a weather test with weather theory and weather products. I've been going over our notes. Let's see, I gotta hit a button, something's not right here. Aha. So I've been going over my notes, and I think that we're roughly averaging about 3 class sessions per chapter. That's roughly about what we're getting. So, you know, call that about a week and a half, you know, per chapter. So to try to help everybody out, I have been creating due dates on our assignments in the Blackboard. To help everybody out, I've been trying to spend more time reorganizing the Blackboard to make it more user-friendly and more layout for everybody. So get in there and you know, I put some rough dates down, like roughly we accomplish a chapter usually in 3 class periods or so. So, you know, a lot of the homework assignments that are part of chapter 6, you know, I have them set as a due date that would be 3 class periods from now. And then, you know, the stuff for chapter 7, I have it set up to be 3 class periods from that. So basically, you know, in a week or so, you'll find, you know, the due dates for chapter 6 material. And then in a week and a half from that, you'll find the due dates for chapter 7 material. I have a button selected that lets you turn in the assignment late. So, you know, don't, you know, freak out. It's nice to stay on top of things. It's really nice to even work ahead. But I'm trying to be as flexible as I can with you guys on this as well. So we're about to get into meteorology for pilots. Oh, this is gonna be fun. Look at that. Well, before we even get started, why? Why do we have weather? This is noteworthy. So if you got your pen and paper open, if you got your pen and paper out, it's worthwhile to write this down. Does everybody see the slideshow? Do I have it set up correctly? Maybe? Any feedback?
I can't see the slide.
No, I'm not
I
seeing
see
a
a
slideshow.
slideshow.
Oh my gosh, thank you for, I'm glad I asked. Let me try again. So here's PowerPoint. You guys are clicking this button, screen share. Aha, PowerPoint slideshow. Do I got it? Are you seeing it now?
Yeah, I'm seeing it now.
Cool.
Yeah, I see.
Yeah.
Thank you for the feedback. So the big question is why? Why weather? Why do we have weather? And all weather happens for the same reason. Drum roll, please. Unequal heating of the Earth's surface. So this is noteworthy. Unequal heating of the Earth's surface. All weather happens for the same reason, unequal heating of the Earth's surface. We have land mass, we have water mass, we have farmer's field, we have concrete jungle called the city. Every single one of these pieces of the Earth's surface will absorb and release heat energy in a different way. So for example, the water, the ocean, the lakes, the rivers, the water takes longer amount of time to absorb heat energy. So it takes a long time to heat up. And then that water will hold on to the heat energy for a longer amount of time as well. So it will stay warmer longer. The land mass will heat up really quick. And then later, when the sun goes down, the land mass will give away its heat really quick. So there is no such thing as cold. There is no such thing as cool. There's no such thing as cold. There's only heat and lack of heat. There's only energy and lack of energy. So these are just some physics, science things that we're talking about as we warm our brain up to weather theory, and then eventually weather products. Meteorology for pilots. So all weather happens for the same reason, unequal heating of the Earth's surface. All right, so I'm watching the clock. We're gonna try to get through a few slides and then we'll take our break. Nobody has to pee their pants. We have good slides here. Look at these good looking slides. It's all about the atmosphere. Oh yeah. So we got a mixture of gases that surround the planet located within the first 1,000 feet of the surface. There are 4 layers of the atmosphere: troposphere, stratosphere, mesosphere, thermosphere. You should know those levels of the atmosphere. By all means, you should. What are things you really need to know? You need to know that we live in the troposphere. We fly in the troposphere. 99% of all weather occurs in the troposphere. So that first layer of atmosphere, you know, roughly on this picture here, they're showing it to be about 20,000 feet. I'll move my mouse around. It should be on top of that. Troposphere roughly could be 2,000 feet. But remember, our atmosphere is like a balloon. It can expand and it can contract. So like in the summer, in the middle of the heat of the day, our atmosphere expands. In the winter, in the middle of the night, the atmosphere shrinks. So the troposphere in this slide says 20,000 feet. I think there's an FAA written question that asks what is the typical height of the top of the troposphere in the mid latitudes. And I think that their answer on the written is 37,000 feet. So there's kind of quite a big difference. This slide says 20,000 feet. I've seen some other slides, some other FAA documents that say 37,000, 35,000. So it really just depends. Most of your airliners are going to fly in the troposphere. All of our general aviation aircraft are flying in the troposphere. So it is very rare. There are some very slick jets that can get up in the stratosphere, but very, very few airplanes get up into the stratosphere. So just to recap, we live in the troposphere, and the next layer of the atmosphere is called the stratosphere. Mesosphere and thermosphere, those are extra way high up there, and unless you're getting involved in space travel, commercial space operations, then we're probably not going to be doing a whole lot of business with the mesosphere and thermosphere. And as far as weather goes and weather theory, 99% of our weather occurs in the troposphere. What you're learning is that these layers of the atmosphere are separated by certain phenomena. There are certain characteristics that happen when you transition from troposphere to stratosphere. There is a boundary layer in the atmosphere that exists between the troposphere and the stratosphere. That boundary layer is called the tropopause, P-A-U-S-E, tropopause. So the tropopause is the boundary layer between troposphere and stratosphere. How do we know where the tropopause exists? The answer is a temperature inversion. Temperature inversion. So where the troposphere meets the stratosphere, we see a temperature inversion. What does that mean? Inside the troposphere, where we live and we fly, and 99% of weather is, inside the troposphere, as we climb in altitude, we typically see the air get colder. We call that standard lapse rate. We typically see the air get colder 2 degrees Celsius for every 1,000 feet that we climb. Once you reach the tropopause, once you reach the boundary layer between troposphere and stratosphere, that is no longer true. It no longer decreases 2 degrees Celsius for every 1,000 feet. In fact, it might slightly get warmer, a half a degree. It actually starts to get slightly warmer, or even maybe just stay the same temperature instead of continuing to decrease and get colder. So they call this an inversion. They call it a flip of the lapse rate. The lapse rate flips. The lapse rate inverts. There is a temperature inversion that exists at the tropopause. That is the boundary layer between the troposphere and the stratosphere. It creates a cap, C-A-P, creates a cap on that layer of the atmosphere, and it traps all of the weather beneath the tropopause. There is only one serious, you know, there's only one serious thunderstorm that can grow so tall that it can bust through the troposphere, and that's called a supercell. A supercell is basically a thunderstorm that's so strong that it produces tornadoes. I mean, very, very strong thunderstorm. So very rarely do you see weather, like severe weather thunderstorms, that are so strong that they can bust through the tropopause. And if there is weather that strong, then it is very serious weather, and you don't want to fly anywhere near that. And it is capable of some very nasty things like tornadoes and hail. So we are warming up our brain to the thought of weather theory. All weather happens for the same reason: unequal heating of the Earth's surface. There are only 3 elements to weather. Ooh, there's only 3 elements to weather: temperature, pressure, and moisture. That's it. It really boils down to that simple. There are only 3 elements of weather: temperature, pressure, and moisture. All energy comes from the sun. So all weather happens because of unequal heating of the Earth's surface. Different layers of planet Earth absorb and release heat different ways. So there's your temperature change. So you're seeing different areas of Earth have different temperatures. Because the different pieces of Earth have different temperatures, that creates different pressures. Because hot air and cold air have different pressures. When you have different pressures, that's what creates wind, because all energy wants to move from high pressure to low pressure. And then moisture is going to be how we get precipitation and actually have extreme weather events like rain, hail, snow, thunderstorms, because moisture is like a small battery. Moisture, a single molecule of moisture, acts like a battery. It can absorb or release heat energy. And then through the process of heat exchange, latent heat energy, then we start to see all the different physical processes, physics that occur as we exchange heat energy, you know, and change from being like a solid ice cube to a liquid water molecule to becoming a water vapor, or a cloud, which is actually a physical water droplet being suspended in the air on top of a piece of condensation nuclei, a piece of dirt. Goodness, a lot of information. So this is the very first slide. I'm warming you up to all the topics about aviation, weather, in this case meteorology. We started with the atmosphere. We discussed the different layers of the atmosphere. We understand that the troposphere is where we are, and that's going to extend up. And we will cover this next slide in a moment. So I'm going to push pause on our slideshow. And if anybody has any general questions, I'm happy to address them. Nobody's speaking up. So we're going to take a 10-minute break. We'll be back in 10 minutes, and we're going to continue on with weather. I'm reading this email about the emergency grading options that you were talking about. It's kind of interesting. I only received 11.
Yeah, you see why I was curious about it.
Yeah, I only received it 11 minutes ago. You must have received it way earlier than me. Did you get it like right when you asked the question?
No, I got it yesterday, like 6 o'clock or something.
Yeah, I got mine yesterday too.
Huh. It looks like it's directed to y'all as students. So it looks like on my end as instructor, I don't do anything differently. I just still issue the letter grade. And what it looks like is that, you know, if you're a person that worries about your GPA, which I mean, I think everybody should worry about their GPA, but, you know, some people may or may not care so much whether they got an A or a B or a C or whether a 4.0 or 3.5 or 3.0. So one of the things I'm reading is that if you as the student select pass fail, then the class does not count towards GPA. So maybe like if you were a student that was, you know, getting a 4.0 and suddenly having to do distance education was going to screw you up and it was going to hurt your 4.0, then maybe you would want to possibly go pass or fail. So that way that one class that screwed you up doesn't hurt your 4.0 maybe. Or maybe if you were a student that had the sickness and you were down in a hospital bed and you could not, you know, physically do the homework to go to class. I don't know. It's a really strange thing. So it sounds like it's something you always click on your end. And I think I would just encourage everybody to probably go as normal, which is to get a letter grade, you know, for the course. I mean, I think we're still doing everything that we can. We're still having meetings. We're still having abilities to ask and answer questions. We're still having homework assignments and tests. So I don't think it's going to affect this course so badly. But you can imagine there are a lot of hands-on courses like the flight labs, like the actual one-on-one flight courses. And for you guys, I think the best thing for you to do is just stick with the normal letter grade, because our department's going to have to issue a lot of incompletes anyway. And I would anticipate that we're going to be, you know, like gangbusters, like just doing a whole lot of flying once summer hits, and everyone's going to, you know, get a lot of hours in, you know, once we have some good weather and, you know, we're cleared to fly for this summer. So I'd hate to see you like, you know, screw yourself out of getting a lot of good flying in this summer because you click a wrong button at this point. Strange. Well, it seems like everybody's had a chance to go to the bathroom, grab a bite to eat. I'm opening up my digital grade book on my iPad. We said that earlier we never saw Charles. Did Charles ever make it in? Charles did not. I don't see him. And Dylan Sims. Oh, you are here, Dylan?
Yes, I am.
Gosh, you must have snuck in on me after I already hit the record button. You're very sneaky. All right. Cool. Well, was there any thoughts or questions or comments from the group before we get excited about some weather? So I'll hit this button. So this is kind of where we left off. We're talking about our atmosphere. We love it. We care about it. It's the only one we got. And different levels of the atmosphere. The troposphere extends from the surface to roughly, it says flight level 360. So you call that 36,000. So again, the slide in the book says 20,000. I think this slide says 36,000. I think there's a written test FAA question that says 37,000. So it really just depends on the season, depends on your latitude. If you live at the North Pole or the South Pole, then your troposphere, your tropopause will be very low because it's so cold. If you lived at the equator, your troposphere would extend very extra high. Tropopause would be extra high because it's so hot. More things about that tropopause. That tropopause is where the jet stream lives. So it's like an area of convergence where all the different winds of the different altitudes get forced into a funnel, like a channel, like a river, and the jet stream lives at the tropopause, which is the boundary layer between the troposphere and the stratosphere. So I'm reading these slides. It tells us that the tropopause acts like a cap to keep the weather down. We call that a temperature inversion. We call that where the lapse rate flips. The stratosphere has the same composition as the troposphere, but no weather. So what kind of things would be up in the stratosphere? Like weather balloons, spy planes. The mesosphere, where the meteors start to burn, and the thermosphere, where the northern lights, are the last two layers, and they have little influence on weather. The atmosphere. Basically, you're talking about the composition of the atmosphere. It's mostly nitrogen. I think it's like what, 70% nitrogen. So most of our air that we're breathing is actually nitrogen. All right, I'm clicking buttons, seeing if we can get this thing to go. Oh, there we go. Composition of the atmosphere, 78%. Ooh. So the atmosphere is approximately 78% nitrogen, 21% oxygen, and 1% other gases. So 78% nitrogen, that's a lot. 21 oxygen. A cubic foot of the atmosphere contains between 0 to 4% of water vapor, which is responsible for the major changes in weather. So think about this. Cold air cannot hold as much moisture as warm air. Warm air can hold a lot more moisture than cold air. So think about Indiana winter. Indiana winter, how do you describe Indiana winter? Gray. It's all gray. There's gray clouds. It's cold. So the cold air cannot hold as much moisture because it's so cold outside. So when the air can no longer hold any more moisture molecules, then it spits out that moisture. It condensates out that moisture in the form of clouds, condensation. There's always small pieces of particles floating in the atmosphere that can gather water droplets on them. That is called condensation nuclei. Condensation nuclei. It is a physical surface for a water droplet to bead up on. It is one of the necessary elements to create a cloud. So we create so much pollution on planet Earth that it's not a problem. There are so many, small particles in the atmosphere, pollutants, dirt, dust, everything, that there is plenty of condensation nuclei for water droplets to bead up upon. So in the cold winter, the air cannot hold as much moisture. So we see clouds form at a lower altitude. As the air cools, because the air, as we go up in the atmosphere, the air gets colder, 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 and the colder air cannot hold as much moisture. So we see the clouds form at lower altitudes in the winter. On the other hand, in the summer, there is a lot of water that can remain suspended as water vapor in the air. Warm air can hold a lot more moisture. So you imagine like warm air, all the particles spread out and there's more space for water molecules. In the summer, as we climb, every 1,000 feet that we climb, we expect the air is roughly going to get 2 degrees colder. And as it gets colder and colder and colder, you get to a point where the air is so cold, it can't hold those suspended water vapor any longer. So then that's when we see the clouds form and condensation happens on that condensation nuclei. But it'll typically happen at higher altitudes in the summer. Okay, so composition of the atmosphere, we're mostly nitrogen, 78%, 20% oxygen, and 1% various others. And then here we are talking about water vapor. And as we keep going, we're going to learn how water vapor can absorb or release energy in the form of heat. All right, so we're on atmospheric circulation. So atmospheric circulation is the movement of air relative to the Earth's surface. All weather on Earth is a result of a heat exchange. So a lot of people think about this with terms of the ocean. You know, there are certain circulations, water currents that transfer heat energy throughout the ocean. You know, it's like the ocean is huge, right? The ocean is huge, but yet it could still have like an average temperature, you know, that might be similar across such a large area because that fluid is circulating. So as that fluid circulates, it transfers heat energy throughout the whole body of fluid. The similar thing can happen with the atmosphere. But wait a minute, the surface of planet Earth, like a landmass cannot have circulation. Land mass is so dense, like dirt, concrete, forest, field, that dirt, that concrete, that forest, that field is so dense, it's not going to circulate. It's not a fluid. So that's one of the big reasons why the land mass is not going to be able to maintain its heat very long. It'll heat up real quick because you're only heating up, you know, the top inch or so of the land mass, and it'll cool off real quick because there's no circular patterns, there's no circulation of that heat energy. It's all just the very upper atmosphere, the only upper layer of the actual land mass. So water is a fluid, yes. Air is a fluid, interesting. So hydrodynamics, aerodynamics. A lot of the same principles apply to hydrodynamics as similar to aerodynamics when we talk about drag, things of that nature. But the big difference is that water is not compressible. Let's say it this way, fluid. Fluid is not compressible, but air is compressible. So that's a big piece of the puzzle that we're going to learn more as we keep going as well. So atmospheric circulation, all the air in our atmosphere can circulate. There is a certain circulation pattern that happens. For us, we're going to see a lot of that circulation pattern happen from west to east. So if you're taking notes and you're trying to hit the big points, this is a big point. Our weather in America moves from west to east. Typically, our weather patterns move west to east. So you see a crazy weather system that's happening out in California or Colorado, it's only a matter of time before that weather system makes its way here to Indiana. We have bad weather in Indiana, it's only a matter of time before that bad weather makes it out to the eastern side of the country. So atmospheric circulation, the movement of air relative to the Earth's surface. All weather on Earth is a result of a heat exchange. All right, so we're now suddenly starting to talk about heat exchange. So the whole idea is that there's only 3 ways for heat exchange. There's only 3 ways for heat energy to transfer. There are 3 ways for heat energy to transfer. These are big, big topics. 3 ways for heat energy to transfer. The first one is going to be called radiation. Radiation would be like the sun, solar radiation. So like the sun puts off these really short beam, you know, energy waves. It penetrates the atmosphere. It penetrates the clouds. You can get a sunburn on a cloudy day because that solar radiation will just shine right on through. Radiation, that's your microwave, is transferring heat energy through radiation, short wave energy waves. So that the land is going to heat up because of the sun. And then at night, when the sun goes to bed and we lose temperature outside, all this heat energy transfer wants to equalize. So now the land mass, it was hot from the solar radiation of the day, and so then later on, the land will start to give off that heat. The land will give up its heat and release its heat, and that would be called terrestrial radiation. So what you're learning is the difference between solar radiation and terrestrial radiation. So terrestrial radiation is long wave energy. It's long wave energy that the Earth gives off after it was heated up first by solar radiation. Solar radiation is short wave energy and it can penetrate clouds, yes. Terrestrial radiation is long wave energy, and no, it cannot penetrate clouds. This is what they call the greenhouse effect. So when you study a lot of the global warming problems, which is a huge topic in the world nowadays, global warming is all about solar radiation versus terrestrial radiation. And we get what's called the greenhouse effect. And our ozone layer has a lot of holes that are burned up in our ozone layer. So we're actually getting extra solar radiation nowadays. That's a bigger topic for another time. So the topic I'm trying to get at right now is the different ways to transfer heat energy. There are three ways. There are three ways to transfer heat energy. The first one I discussed is radiation, solar radiation, and terrestrial radiation, the shortwave and long wave energies. Another way to transfer heat energy is called conduction. Conduction, and that's like physical touch. Physical touch. Something's very hot and you physically touch it. Gosh, that heat is now physically transferred. Physical touching is called conduction. That's more of like your stove, how your stove works when you heat up the burner and then put the pan on the stove. Conduction. If you light the end of a metal rod, the other end of the metal rod gets hot because of physical touch. Electricity flows through the wire, heat. So three ways to transfer heat energy: radiation, conduction, and convection. Woohoo! We made it to convection. So convection is going to be the largest topic for the conversation of weather. But you know, as people who study physics and airplanes and physical processes, we need to realize there are three ways to transfer heat energy. Three ways to transfer heat energy: radiation, conduction, and convection. As we study weather theory, the majority of our weather theory is going to revolve around convection. Convection is the transfer of heat energy through circular fluid patterns. And when I say fluid, I am talking about the atmosphere or the ocean. I'm talking about air or water. Convective currents. There are convective currents that transfer the heat energy. This would be very similar to your house, where you have an air conditioner or a heater. Like it's getting hot outside, people are turning their air conditioners on for the first time, and you only got maybe one air duct in your bedroom, but yet it still cools the whole room because the transfer of heat energy, the air in your room circulates. So circular patterns of heat energy transfer, that is called convection. That's what this slide is all about. I read it. Heat is transported or circulated from one latitude to another. As air heats, it expands and then rises. As air cools, it contracts and it falls. The process of air movement is called convection. If I could rewrite this slide, I would call it fluid movement, because not only is it the air movement that we can have convective currents, but we can also have it in the water as well, convective currents in the water or the ocean. So this slide right here is showing us a good convective current. We got a solar radiation that heats up the land. The land then has an updraft. They call that a thermal. And it says as the air warms, it becomes less dense and rises. This is called a thermal. We have a convective current of rising air called a thermal. And that hot air rises. We know standard lapse rate says we expect the air to cool roughly 2 degrees Celsius per 1,000 feet. So as that air rises, it cools. And then as the air cools, it actually becomes more dense, so then it wants to turn around and sink. That cool air sinks, and as it gets to the lower altitudes, it warms back up. And in this case, we actually have a picture that shows the difference between a water mass and a land mass. The land mass heats up really quickly because down here where my mouse is at the very bottom of the picture, you're not where it's black, where it's really dark, deep red. That piece of Mother Earth, that piece of dirt and soil is not seeing any of the solar radiation. The only pieces of the soil that's receiving the solar radiation is the very top surface. So the very top surface of planet Earth is heating up really quick, but the deeper surfaces are not. There are no convective patterns. There's no convective transfers of energy in the landmass. So the water mass over here on the right side of the slide, where it says cool sea and there's some happy fishes here at the bottom, there are convective currents that are occurring in that water mass. So the water mass is going to maintain more of an equal temperature for a longer period of time, whereas that land mass is going to see a lot of changes. In this picture, we have a cooler sea and a warmer land, and so you would call this a sea breeze, as the air flows from the sea to the land, and then that's where we're going to see then the thermals pick up the hot air, and then we establish this convective circular current of heat energy transfer. There are only 3 ways to transfer heat energy: radiation, conduction, convection. Convection is the big one, and here is a convective current cycle that I've explained very thoroughly. Whew! You probably don't want me to repeat that again. I said that a few times, huh? Okay, so here's a bigger picture of what's going on. In the bigger picture, we have this exact same process happening over the whole planet Earth. So there are, in this picture, it's showing 3 cells. We have what's called a Hadley cell. We have what's called a, they're not listing the other 2 right here. I don't want to tell you the wrong names, but there's a cell, there's cell 1, cell 2, and cell 3. So let's just read the slide to start with. 3 cells per hemisphere that help distribute heat energy, okay? In the Hadley cell, warm air rises and moves towards the poles. The air cools and sinks back towards the surface where the pattern is repeated. Okay, so they first start with the Hadley cell. Oh, somebody's typing. Somebody's chatting. Hadley, Ferrell, and Polar. There it is. Jake's done his homework. He's got it looked up. Thank you, Jake. Perfect. So here's our Hadley cell. This would be the Ferrell cell, where my mouse is circling. And this would be our Polar cell, where my mouse is circling. Awesome. So the idea is that there are going to be areas, I don't want to be too complicated. I'm trying to work you up to it. So the idea is that here's the Hadley cell. Warm air moves towards the equator. And then in the equator, I get an area of lifting force. And see how the atmosphere is going to be extra tall here at the equator. And then as that cooler air travels north, the atmosphere gets smaller again. It shrinks down. This is the Hadley cell circulation pattern. And what you're learning is that down here at the equator, we get an area of rising air. Here at the equator, we get an area of rising air. That would be called low pressure. So what you're learning is that you're going to have areas of different pressure. We said there's only 3 elements of weather: pressure, temperature, and moisture. There's only 3 elements of weather. If you haven't wrote that down yet, now's the time. 3 elements of weather: temperature, pressure, and moisture. Here at the equator, we're getting an area of low pressure. Low pressure. Low pressure is a lifting force. So the air is being lifted aloft here at the equator. In the Hadley cell, we're seeing that air move north, and then the air sinks down. They call it the horse latitudes. They call it the 30-degree latitude. They call it the subtropical high. So right here around 30 degrees of latitude, where my mouse pointer is, and I'm circling it, subtropical low, horse latitudes. There becomes an area of sinking air. You have sinking air from the Hadley cell. Moving up here and looking at that Ferrell cell that we talked about, or Ferrell cell, whatever it may be, you're seeing a very similar circulation pattern happen, but it's almost in reverse. So in that Ferrell cell, you're seeing sinking air happening at 30 degrees of latitude. The Hadley cell was showing sinking air at 30 degrees of latitude. So at 30 degrees of latitude, we have developed an area of low pressure. I said it wrong. Damn the bad luck. There's 2 types of pressures: high pressure and low pressure. At the equator, we're seeing low pressure, and that's where air rises. At the 30-degree latitude, we are seeing high pressure, and that's where air is pushing down. Now we're at the top of planet Earth. We're seeing another area of rising air. So that would be a low pressure area. And that is where the polar cell meets the feral cell. And that's happening at roughly 60 degrees latitude. So why do we care? It's all about these circulation patterns. And what's interesting to notice, we said that in planet Earth, we're seeing movement of weather in America. In America, we're seeing movement of weather from west to east, from California to New York. And we have two jet streams, two jet streams that could influence our weather here in America. We have a polar jet stream, which roughly happens at that low pressure area, which would be 60 degrees latitude. That's where the polar jet stream is going to form and travel from west to east. At the 30-degree latitude, where that high pressure area forms, that's where you're going to see the subtropical jet stream. And then those jet streams will move west to east. The jet streams are a high altitude phenomena, and they're going to really influence that flow of fluid, that flow of air mass as we transfer energy from the west to the east and study our particular weather circulation patterns. We live in an area called the prevailing westerlies. We live in an area called the prevailing westerlies, and all of our weather is moving from west to east. I don't want to say all, but 99% of our weather moves from west to east. There are these old phrases that grandma used to tell us about weather. And one of the phrases that grandma used to tell us about weather, or you could look it up in the Farmer's Almanac, is a phrase, if it's from the east, it's a beast. You've heard that, right? If it comes from the east, it's a beast. E-A-S-T, east, beast, B-E-A-S-T. So if you have a weather system, if you have a storm, if you have a weather system that's moving from the east to the west, then that sucker is a beast, B-E-A-S-T. It is a super strong weather system, and you don't want to go flying near that thing because it is fighting all of our prevailing westerly weather. So we live in an area prevailing westerlies. Our weather systems move west to east. If you see a weather system that's coming from the east to the west, it is a beast, and you don't want to fly into it. Think about like hurricanes. Like when you got very, very strong hurricanes that are coming from the east to the west, that everybody wants to flee the area and call it a disaster because nobody wants to battle with that. So this is a very big conversation about convection. Convection is the transfer of heat energy through circulation patterns, and here's some of the circulation patterns that we're going to encounter in our neck of the woods called America. Things to notice is that if you go fly airplanes south of the equator, if you go and spend your life living south of the equator, it is an exact opposite mirror image of everything that we see up here in America. So, for example, if you flush the toilet in the southern hemisphere, the toilet flushes the opposite direction than it does here in Indiana. Any questions about this slide? I feel like I'm really spitting a lot of information out. All right. Some interesting notes. They call this equator the doldrums. And they actually can call it the ICTZ, Intercontinental Tropical Zone, something like that. I'm probably saying it wrong, but it is the area where some of the worst thunderstorms develop. So you hear about all these like Air Malaysia flights, and you hear about all these airliners that go down and nobody never knows what happens to them. A lot of the beliefs is that there was a very serious weather event that resulted from an ICTZ, which is basically some uplifting force that developed in this area of strong lifting force. All right, let's see what the next slide has to tell us. Atmospheric pressures. So we've been starting to get into this topic. Temperature, pressure, and moisture. There's only 3 elements to weather. Awesome. Temperature, we've covered that. Temperature, the different surfaces of planet Earth absorbing and releasing heat in a different way. You got to also think about how like the Earth is tilted on its axis. There are certain areas that receive more sunlight than others, talking about the North Pole versus the equator, Florida versus Indiana. So we start to see all these temperature differences. Well, differences in temperature can influence and create differences in pressure. And that's what this slide says. Changes in heating also cause changes in pressure. So if you were studying a chart, you could see the different changes of pressure. They say equal areas of pressure are connected by lines on a chart called isobars. You will have test questions on this vocabulary word, isobars, I-S-O-B-A-R-S, isobars. So areas of equal pressure are connected by lines of isobars, okay? If you study the patterns of those isobars, it reveals the pressure gradient. So that's another big vocabulary word, pressure gradient. In fact, they say the word pressure gradient force, pressure gradient force. So the idea is that if you have a bunch of isobars on a chart that are very close together, that means there is a very strong change in pressure in that area. If you're looking at a chart and there is very few isobars, they are very few and they are spread out over a very large area, that means that there is not very much change in pressure. So pressure gradient is describing the amount of change in pressure over that area. If there is a lot of change really quick, you call that unstable. If there is not very much change, then you call that stable. So we're starting to introduce the idea of stability. And if there is a lot of change in a very short amount of time and space, then it is unstable. A lot of change, unstable. If there is little change, then it is stable. So if we see the isobars all on top of each other, if we see all isobars close together, there's a lot of change in that area, it is less stable, and the pressure gradient force is very strong. The pressure gradient force is very strong. The pressure gradient force is what causes wind. So the air mass wants to move from the area of high pressure to the area of low pressure. And so one of the factors at play is pressure gradient force. All right, pressure gradients are divided by types in the areas. We could have a high, which would be a concentrated area of high pressure, which means everything surrounding it is lower pressure. You would notice this on a chart by a big red H. Big red H, that is an area of high pressure. What do you need to know about high pressure? This is noteworthy. What do you need to know about high pressure? It rotates clockwise. What do you need to know about high pressure? This is important. It is stable. What do you need to know about pressure? It is a sinking force. So high pressure lives high in the atmosphere, it pushes down, it's a sinking force, it creates stability, and it rotates clockwise. High pressure, very important. You need to know that to get through all your check rides and the test. High pressure. Next up, low pressure. A low pressure center, a low is a concentrated area of low pressure surrounded by low pressure on all sides. Okay, so a low pressure center on the chart typically would be a big blue L, a big blue L. What do you need to know about low pressure? Think about the L's of a low pressure system. It is left-hand turning. It is more lousy weather. It is less stable. It is lifting force. The L's of a low pressure center. Big blue L, left-hand turning, that means counterclockwise rotation. A low pressure center is counterclockwise rotation. It is a lifting force. Why do we care? Because a lot of extreme weather requires lifting force. Low pressure. Let's talk about visibility. A low pressure system actually has better visibility. Ooh, that's kind of interesting. You don't say. Yeah, a low pressure system actually has better visibility. Because it's a lifting force, it's lifting all the dirt and debris and pollution and particles and dust. It's lifting all that crap out of the way, and you can see through the lens of the atmosphere more clearly. A low pressure system allows you to see farther. Low pressure system. A high pressure system, on the other hand, is actually going to be less visibility, because a high pressure system lives upper in the atmosphere and it's pushing down, and all the dirt, debris, pollution, dust, condensation, nuclei, all the crap that's in the air is being trapped by that high pressure system. And so the lens that we look through, called the atmosphere, is more dirty, and you cannot see as far visibility on a high pressure day. I'm not talking about visibility that we measure, 10 miles visibility. I'm talking about visibility that you see with your naked eye when you're flying an airplane. Like, there are certain days where I can see Terre Haute from Indianapolis, 50 miles away. That would be a low pressure day. On a high pressure day, I might only be able to see Greencastle, maybe 20 or 30 miles away. High pressure systems and low pressure systems. Very huge conversations. In fact, there's some new homework that's been posted, some new homework assignments where you do the short answers, and all that information I just spoke to you is one of your questions that you're trying to figure out right there about high pressure systems versus low pressure systems. More vocabulary words. We got something called a ridge. A ridge is an elongated area of high pressure. A ridge is an elongated area of high pressure. We say the words elongated area. Some folks would say the words a line. It is a line of high pressure. What do we know about high pressure? It lives up in the atmosphere and it pushes down. So what do we know about a ridge? It is a stable phenomenon. It's causing sinking air. It resists any sort of lifting action. So a ridge is an area of stability. It's air that's pushing down. It resists vertical motion. Ridges are not that common on the chart. The next vocabulary word is a trough. A trough is an elongated area of low pressure. What do we know about low pressure? It is a lifting force. We know that it is less stable. So in that trough, it's an area of lifting force. It's less stable. We could possibly see some weather develop in those areas because lifting force is one of the elements to create severe weather, hazardous weather. Trough. A new vocabulary word, col, C-O-L. A col is a neutral area between two highs and two lows. Col, C-O-L, a neutral area between two highs and two lows. So you're going to have test questions about these topics. So imagine a low pressure center. So a low pressure center, I wonder if I can draw. I wonder if it's in my next picture. Oh, here's the next picture. I like this. Okay, I'm going to try to draw with you guys. So annotate. And I'm going to draw. And what color should our airplane be? Nobody has any preference.
Let's go for red.
Oh, we want a red airplane today. I like it. Thank you for the participation. So you're going to have some tricky test questions about this on the FAA written exam. And so let me try to draw an airplane. I can do this. Come on. Yes, look at that airplane. It's looking good. It's looking like a good airplane. I'm liking it. There it is. Okay, look at that airplane. And the airplane is traveling forward towards the center of that low pressure. Everybody's with me. You're going to have a tricky test question that talks about how you have a crosswind from the left. It says you're experiencing a crosswind from the left. And you'll have to be able to figure out, does that mean that you are heading towards the center of a low pressure center? Does that mean you're traveling away from the center of a low pressure center? Does that mean you're traveling towards, into a high pressure center? Does it mean you're traveling, you know, I just gave you 3 options, right? I said you're traveling towards a low pressure center. I said you're traveling away from a low pressure center, or I said you're traveling into a high pressure center. So if you had a crosswind from the left, then the answer is you're traveling into the low pressure center, just like we have depicted here. Because if I was traveling out of the low pressure center, the crosswind would actually be from the right. Does that make sense?
Yeah, it makes sense.
And then if I was traveling into a high pressure center, the crosswind would be from the right. So in those 3 examples I gave you, I'm preparing you for some written exam questions that exist. And they'll tell you that you have a certain wind from a certain direction, the left or the right, and then you'll have to guess A, B, or C. Does that mean we're traveling towards a low pressure center, you know, towards a high pressure center, away from a high pressure center, away from a low pressure center? And you have to have some understanding of the fact that low pressure centers rotate counterclockwise. High pressure centers rotate clockwise. And again, a low pressure center, the L's of low pressure, it's left-hand turning, it's lifting force, it's more lousy weather, it's less stable. High pressure center, it's more stable, it's up in the atmosphere pushing down. Clockwise rotation. Okay, so I'm clearing the pictures that I just drew. I'm trying. And these are some graphic images of the topics we've already been discussing. High pressure and low pressure. Over here on the left, we're talking, these are pictures of isobars. These are isobars. Actually, down here in the bottom, these are isobars as well. So isobars on the weather chart are measured millibars. So there are many different units of measurement that we need to be responsible for. We're talking about pressure right now. There's only 3 elements: temperature, pressure, and moisture. Right now, we're talking about pressure. Pressure, as pilots at this stage of the game, a lot of the history that you have, a lot of the experience you have dealing with pressure is in inches of mercury. Inches of mercury. We know standard pressure is 29.92 inches of mercury. We know that as we climb every 1,000 feet, we expect the pressure to decrease 1 inch mercury for every 1,000 feet. Okay? But now we're looking at all these weather products. These weather products are showing us that pressure is often documented in a new unit of measurement called millibars, M-I-L-L-I-B-A-R-S, millibars. Millibars is more of like the international standard unit of measurement for pressure. 2 inches of mercury, that's more of an Americanism, a USA unit of measurement for pressure. Just kind of like how America, we have like feet and inches, and the rest of the world has meters and centimeters. So in America, we have 2 inches of mercury, but a lot of the rest of the world studies pressure in terms of millibars, M-I-L-L-I-B-A-R-S, and the standard pressure for millibars is 1013.2. You need to know this. 1013.2. 1013.2, 1013.2. That is the standard pressure level at sea level in millibars. So what you can see on some of these charts is the pressure gradient. You can see the isobars and how the pressure is changing over the course of the region. So my mouse is on this top left picture, and it looks like this is Michigan, Lake Michigan, Wisconsin, Minnesota. And over here in northern Michigan, we have an isobar of 1004. That is a low pressure. Why? Because standard pressure is 1013.2. So 1004 is low pressure. So low pressure would be a counterclockwise rotation. So you would expect the winds in that area to have this counterclockwise flow, like my mouse is doing, a counterclockwise rotation. And then as we get farther and farther away from that low pressure center, we see the isobars they have larger values. So 10, 12, 10, 20. So over here, 1020, we are now above the standard of 1013 decimal 2. So now over here on the 1020, we are dealing with an area of high pressure. So in the area of high pressure over here with 1020, we are expecting to see more of a clockwise flow, airflow, as you can see me doing with my mouse. So that was us describing and studying the pressure isobar changes, millibars, in the top left picture. Let's take a look at the bottom picture. I want you to compare these two low pressure centers. So we have a low pressure center here under my mouse that gets all the way down to 975. That's very low. Remember, the L's of a low pressure system rotates counterclockwise, so it'd have this counterclockwise flow like my mouse is doing. This is your low pressure center, and this would be the wind circulation you expect in this area. It'd be left-hand turning counterclockwise. It'd be a lifting force. It'd be sucking air up. It'd be more lousy weather. You might have a little bit better visibility though. Okay? Compare this low pressure center to this low pressure center way over here, far right. This low pressure center, the lowest is 1000 millibars. So it is not as deep of a low. It is not as low of a low. It is not as extreme of a low. It is not as strong. It is not as strong of a low pressure center. And you can see it very visually because there's less isobars. There are less lines circling this low pressure center. So yes, this low pressure center will still spin counterclockwise. It'll still be a lifting force. It'll still have less stability, but it is not nearly as strong as the low pressure center over on the left side of the picture. And what you're really trying to notice and pay attention to is look at how many millibars are surrounding this low pressure center. That means that there is a very strong change in pressure. There is a lot of pressure change over a very small amount of space and time. What does that mean? It means that the pressure gradient force is very strong, that the winds are going to be very strong. Why do we have winds? We have winds because of areas of unequal pressure. So all energy wants to move from high to low. So in this chart here on the bottom that we're studying, I have a high pressure center on the very far left. Its isobar is 1030. High pressure rotates clockwise. So this would be the rotation you would expect to see from this high pressure center. And all energy wants to move from high to low. So as the air tries to move from the high pressure center to the low pressure center, there is such a strong change in pressure along the way that you're going to see very, very strong and fierce winds in the areas where the isobars are close together. Whew. I promise I'm doing my best to really take my time and explain it to you. What are your guys' thoughts about some of this weather talk?
Will the higher low pressure move towards the lower low pressure system?
All energy wants to move from high to low. So the simple theory is that all energy wants to move from high to low. Remember we learned about lift and the wing, and we said that the wing has an area of high pressure beneath and an area of low pressure above. And so like when we have our wing and we hold our arm out, we have an area of high pressure beneath and we have an area of low pressure above, and that high pressure wants to get to the low pressure, and so it's pushing up. It's like high pressure is desperately, madly in love with that low pressure. That high pressure thinks that that low pressure is super sexy and hot, and that high pressure wants to get to that low pressure. So I got this area of high pressure down here, and I got this area of low pressure up here, and the area of high wants to get to the area of low. But we have a wing, a physical barrier that's in the way that prevents the high from getting to the low. And so when that high pressure is pushing up against the bottom of the wing to try to get to the low pressure above, that's one of the reasons we create lift. That's Brunelli's principle of differential pressure. We are now seeing a lot of that same concept happen in the atmosphere. Only now it's over the course of hundreds and hundreds of miles instead of just a few feet. So trying to answer your question, The high pressure wants to go to the low pressure, yes, but there's a lot of reasons why the high pressure can't just run straight to the low pressure. We're going to talk about something very soon called Coriolis force, how the Earth is spinning, and because the Earth is spinning on its axis, it's going to create a lot of issues with the flow of high pressure to go straight to low pressure. We could talk about geography. So like in studying United States of America, we have huge mountain ridges, like the Rocky Mountains. And so all of a sudden there are physical barriers that can prevent high pressure from actually making it to low pressure. So there are weather systems that can develop, you know, like crazy large thunderstorms. There are air masses that can get in the way of other air masses. So I want to answer your question. Your question is that, does the high pressure want to go to the low pressure? Yes, in theory, the high pressure wants to seek out the low pressure. This whole world is just in a constant state of trying to achieve equilibrium, but for whatever reason, there's always these other factors why we can't achieve equilibrium. Everything can't always be 100% peaceful. And so the high pressure wants to find the low pressure and achieve equilibrium, but there's a lot of factors that go into play, and that's why even the weatherman can't always get it right. So I don't know if I actually answered the question or not.
Yeah, you got the answer. Thank you.
Yeah. So I'm looking at my clock. I'm at 12:29. So I don't think I should click on another slide and open up another can of worms. But if there are more questions about anything we've done so far, you know, I'm here to help answer any of your questions. Another thing that the university is getting all excited about is it's called Blackboard Collaborate. So our flight department has already got me set up doing Zoom, and we're already set up doing Zoom. So we're just going to keep doing Zoom. It's a great thing. It's awesome. We're going to use Zoom. It's working. Cool. Awesome. There is a very similar tool in Blackboard called Blackboard Ultra Collaborate, where I push buttons on my computer and it video streams my face and my my voice. And we're not flying airplanes right now, so I have it set up so that way I have virtual office hours. So throughout Monday through Thursday, you know, anytime that I'm working on my work here for the university, if I can push record, I'll send out a message and you can log in to the virtual office and you can ask me questions one-on-one through Blackboard with the Blackboard Virtual Collaborate. And then because I'm not flying airplanes right now, on my Fridays, I'm booking it as like a 9 a.m. to 12, so like a 9 to noon, where I'm designating that time where I can be in my virtual office as well, and I push the button. And, you know, I have to push the button and hit record regardless for the university. So if any of you all ever want to show up and, you know, ask me any questions in a one-on-one type of fashion, that virtual office is up and running as well. So my goal is not to hold anybody up. If nobody has any questions, I tell you guys all to have a great day. There's lots of homework. We have homework assignments up for Chapter 6. You know, we're going to be doing Chapter 6 and Chapter 7 together for the test. So feel free to start working on those. And I hope that you guys are having a great day. And get some blue sky out there, soak up some sunshine. Thank you.
Thank you, sir.
All right. Thanks a lot. Have a good one.
Thank you.
Thank you.
See you guys.